So in our last lecture, we discussed the universal covering group, and we actually covered a lot of ground. And this is the drawing. This drawing here is where we kind of left it. We identified the notion of a universal covering group that was a simply connected group, which meant that, of course, its fundamental group was was isomorphic to the trivial group. And the reason I say that is the fundamental group really is this group of paths homotopic to the identity. So that is an isomorphic to the group that just has the identity element for a simply connected space. And then we talked about its discrete invariant subgroups, and there would be a list of them. And then all of the other Lie groups that share the same Lie algebra with this simply connected Lie group are all just factor groups, right? Here's what this stuff here, factor groups of the simply connected universal covering group. And they're each factor groups of the universal covering group by one of its discrete invariant subgroups. And so in this lecture, we're going to try to just show how this story fits with SU2 and SO3. So let's begin. We start with, say, SO3, SU2, and SL1Q. So starting with these three groups, which we've studied extensively. Actually, we studied these two extensively, but we haven't as much. I mean, we developed this group, and we developed... in fact, we developed the unitary group without the special unitary. We developed this group as well. But we have these three groups, the point being that they all shared the same Lie algebra. Right? They all shared, I guess I could call it SU2, the Lie algebra SU2. They all had the same Lie algebra, which means each of these groups, when linearized, gave us the same Lie algebra. So the immediate question is, well, have we found all the groups that give us the same Lie algebra? Right? What was this Lie algebra? Just as a reminder, how did we characterize that? Just to understand what we mean by the same Lie algebra. Well, it all had the same commutation, right? It had the same set of generators. In each case, there were three, and the same commutation relations for the generators equaled... I think we wrote the generators this way. We might have included a minus sign back when we did it. Not positive, but the point is that's the algebra. The algebra is the generators and the relationship between the generators. That's what defines the entirety of the algebra. But all of these, when linearized, gave us the same algebra. And likewise, when we started with a representation of the algebra, these were all linearizations, right? Linearizations. And when we started with the algebra, the exponentiations of the algebra using different matrices that followed these commutation relations gave us each of these different groups, right? And so now we have to ask, well, wait a minute, how do we know that there's not some other group out here, right, that shares all of this, right? That's one question. And then the other question is, which of these is the universal covering group? Well, that question we can answer right away, because we already know that the fundamental group for the group SU2, right? The fundamental group of the group SU2, right? Notice how this works. Pi 1 is the fundamental group. What goes in here is a topological space, right? And this represents the fundamental group of a topological space. Well, SU2, although we think of it as a group, typically it is a topological space because it's a Lie group, and that's what Lie groups are. Lie groups are topological spaces and groups, right? I keep emphasizing that, but there's no reason not to stop emphasizing it because it's something you've got to keep in mind all the time. So with that in mind, we know that the fundamental group of SU2 is in fact the identity, which basically means this is our simply connected group. So let me just erase this. And this being our simply connected group, that gets a little bit, say, elevated, right? This gets elevated, and that is our universal covering group. Let me clean the rest of this stuff up here. All right, so now that we know what the universal covering group is, oh, and it is still true, of course, that the universal covering group, when linearized, gives you the algebra, and when the exponential of the algebra is taken, you can find a representation that gives you the universal covering group. Okay, so now once we know the universal covering group, we want to find all of these guys, right? Including this maybe mysterious one over here. Well, what do we need to do? Well, each of these must be SU2 as a factor group with some discrete invariant subgroup. So we look at SU2 and we're looking for all of the discrete invariant subgroups for SU2. We've got to find it. So let's look for a discrete invariant subgroup. So one example of a discrete invariant subgroup for SU2 is the subgroup that contains the identity and minus the identity. All right? So let's consider that as a discrete invariant subgroup for a moment. So let's first of all remember, we're going to remember that this was SO3. We calculated it. And we also calculated SU2, right? So these are the matrices. This was one form of a matrix expression for every element of SO3 and every element of FU2. So I'm suggesting that SU2 has a discrete invariant subgroup of the identity and minus the identity. And so we look at SU2 and we say, well, first of all, is the identity even part of it? And of course, if you choose theta, basically you choose theta 1, theta 2, and theta 3. Those are the parameters, right? And they come together and form theta, which was theta 1 squared plus theta 2 squared plus theta 3 squared. The square root of that is theta. So if you choose theta to be 2 pi, right? Or 0, actually, you could choose theta to be 0. That's an important fact. If you choose theta to be 0, you get this here will be well, if you choose all three of these guys to be 0, whoops, say you choose all three of these, theta 1, theta 2, theta 3 to be 0, then theta is 0, right? That's how you get theta to be 0, is by choosing theta 1, theta 2, and theta 3 to be 0. So if you do that, then what happens? I think it works, right? You get cosine of 0 is going to be 1. The sine of 0 is going to be 0, but also this is 0, right? So that's this is actually going to be 0 like 0 over 0, so that would be kind of a problem. But the point is this part is 0, so this stuff goes away. So that's gone, and that's gone, and this becomes a 1. So that's the identity. So that's cool. But if you take theta to be, 2 pi, right? If you take theta to be 2 pi, then what happens? Well, then sine theta over 2 at 2 pi becomes sine of pi, which is 0. And so this term goes away. Well, let me undo the other stuff so we can do it again. So this term will go away, right? 2 pi, sine of pi, this whole thing goes away, that whole thing goes away, that whole thing goes away, and then you end up with -1 and -1. Now remember, SU2 is the special unitary group, so you expect the determinant of this thing to be 1. Well, the determinant of that particular matrix will be -1 times -1, which is 1. So that is a member of SU2. So I and minus I are certainly a subgroup. Now, so it's a discrete subgroup because it's got 2 elements. But is it an invariant subgroup? Now, turns out there's no others. This is it. This is not only a discrete invariant subgroup, it's also the center. meaning this is the largest set of matrices that commute with every matrix in SU2. And it has no subgroups except the identity itself. It only has the trivial subgroup. So this is it. So when we go back to this story here, where we'd have a whole bunch of discrete invariant subgroups for this sort of arbitrary situation, in this case, all we have is one, right? So this doesn't exist and this doesn't exist. There's only one other group that we can form, and we're going to form that right now. So we go back to this picture, and we say, all right, so what have we got? Well, there is no other groups out there, right? There is SU2D like this, but now we know what D is, so I'll just erase this, and why don't I just put it in explicitly? I minus I, right? And D over here, I could write it like this. I just write, let's see, I write D equals I minus I, right? So now I know what the discrete invariant subgroup is. And this is going to be, oops, I like black for this purpose, the factor group of SU2 by its discrete invariant subgroup has got to be the only other group that shares the same Lie algebra. That's not simply connected. So remember, the reason I know this is not isomorphic to SU2 is because pi 1 of SO3, right? Remember we calculated what that was. And oh, what was it? What was the fundamental group? It was I minus I. And that is one of our principles, is that the topological fact that the fundamental group of SO3 is isomorphic to integers mod 2, right? Integers mod 2 happens to be the same as the group theoretical fact that the center, or a discrete invariant subgroup of SU2, is also integers mod 2. The fact that this is the same as this is actually a requirement of the theory, and it's this terrific binding of group theoretical properties here in the universal covering group with topological properties regarding connectedness in the discrete invariant subgroup. Remember, the only reason we cared about these topological properties was because it told us that SU2 was the universal covering group. Once we discovered that, because its fundamental group is just the identity, then we go hunting around the group theory looking for a discrete invariant subgroup. And when we found that, we now know that somewhere out there in the world there is another Lie group whose fundamental group is Z2, because it has to match this discrete invariant subgroup. And we already know what that is. That's SO3. Okay, so we've kind of gotten everything worked up, except we have this problem. We have this special linear group of 1Q. We've used up the discrete invariant subgroup. What about this thing? We haven't really studied it. But what's interesting about the special linear group Q is its fundamental group, SL, I should know by now that I need to erase these lines here when I do this, SL1Q, that fundamental group is trivial also. It is also trivial. It is also trivial. So that means that SL1Q is simply connected. And its being simply connected means it is the universal covering group. But there can only be one universal covering group. And we thought we found it, but now looks like there's two. But the answer to that is that this is evidence, or actually this is indicative of the fact that SL1Q is isomorphic to SU2. It's really the same group. It's really the same group. And because of that, there's SL1Q and SU2 are isomorphic. They're in one-to-one correspondence. as groups and as topological spaces. Now, the fact that they're homeomorphic as topological spaces is not proven because they both share, they're both simply connected. There are many instances where groups that are simply connected are not homeomorphic. If they did not share the same fundamental group, you would know that they were not homeomorphic. The fact that they do share the same fundamental group suggests it's possible they're homeomorphic, but you've got to find the homeomorphism. And indeed, SU2 and SL1Q are in fact homeomorphic. And we won't go into the details of finding the homeomorphism. I think we did that actually earlier on in this lecture series. But the point is there are not three groups that share the same Lie algebra, the SU2 Lie algebra. There are not three groups. There are only two groups. And by the way, I'm naming the Lie algebra after the universal covering group. Why not, right? I mean, we could have called this SO3, this Lie algebra, if we wanted to. It's the same Lie algebra, so why not? But we're going to name it after the universal covering group. Okay, so one other thing I want to review is the actual construction of this thing through this, which is not really a thing. I mean, it's pretty easy. In principle, it's just we review it each time, right? We're looking, what do we mean by this operation, this quotient space operation? We're saying that this is the quotient space of SU2 by its normal subgroup I minus I. Well, a quotient space is a set of cosets, right? So I need to create all of the cosets of I and minus I that exist. And when I say exist, I mean all the cosets of SU2 that exist with the normal subgroup I minus I. So I'm going to partition SU2, and I just redraw it here. I'm going to partition SU2, like say this is SU2 here, right? I'm basically taking the coset I minus I, which I'll indicate by this little subset there. That is the subgroup I minus I. And then this is going to partition the entire group up into cosets. And every coset is going to be an element of the group SU2 times I minus I. Right? So just like I did before, this will be A and minus A, and B and minus B, right? And obviously when I draw it this way, I kind of give you the feeling that it's a countable thing, but it clearly isn't, right? Because every element of SU2, which is a continuous group, I mean, that's the whole point, is going to create a coset, is going to be bundled up with its opposite and create a little coset. And every one of those cosets, if I put them together in a big collection, right? If I put them together in a big collection, then I've partitioned SU2. And every element of SU2, say A, will be in exactly one partition, right? It'll be in this partition. And minus A will be in that partition. And B will be in that partition. And minus B will be in that partition. And C will be in that partition. And minus C will be in that partition as well. And every element will be partitioned in SU2 according to, along with its opposite, meaning its multiplicative opposite. So with that in mind, now once you've done that, let me erase this here. I've actually created a set of cosets, right? I just changed the name. Well, I changed SU2 where now this element here, or this coset here, or that coset there, all of these cosets, including this coset, becomes an element of the new group. And this element, the identity element of the new group, will come from the actual normal subgroup. But each coset will become a new element, and I could just call that element A, right? Or I could call this element C, and this element here would correspond to an element B. So each coset is in one-to-one correspondence elements of this new group. But how do I define multiplication in this new group? If I'm going to propose that this thing is a group, and it's going to be isomorphic to this, I have to define the notion of multiplication of cosets, right? And so how do I do that? Well, I say that the coset containing A multiplied by the coset containing B is just the coset containing A times B, right? Where now this multiplication is the multiplication in this new group I'm creating, right? That's this group here, right? And this multiplication, this thing here, that's the multiplication in SU2. That's the old SU2 multiplication. And this defines multiplication in our new group. And this new group ultimately is SO3. And it's interesting, you know, an astute observer of this material posted the other day and actually kind of confused me for a second because I was kind of flummoxed by it. But if you look at this matrix for SO3, what you'll see is that it's impossible to get -1, -1, -1 on the diagonal and 0 everywhere else. And of course, it should be impossible because this is the special orthogonal group. So its determinant always has to be +1. And clearly, the determinant of the matrix I just sort of scribbled out is -1 times -1 times -1, which would be -1. And I think in a previous video, I actually even suggested you could get to -1 in SO3, but you cannot, because even if you took, I'm trying to think how you would do it, you would have to take, first of all, you'd have to take theta to equal pi, right? And then that would be good because then you would get -1, -1, and -1. And then, but as I mentioned before, these would all become 2. All the 1 minus cosines would become 2. All right, so I can scribble all those out as 2. Now, what's important to note, though, is that you always have these factors in front of the 2. So you might say, oh, well, I'll just choose theta1, theta2, and theta3 to all equal 0. But that contradicts this, right? You can't do that. Once you've chosen theta equal to pi, there's some non-zero theta1, theta2, theta3. So you're not going to get this minus the identity element. Anyway, so clearly the identity can be reached, but minus the identity can't be reached. But in this coset group, you're actually taking SU2, you're taking the element that you can reach in SO3, and you're blending it with the element you cannot reach in SO3, right? And you're putting them together in one thing, and you're calling that an element of SO3. And that turns out that's isomorphic. So that's what SO3 is. Okay, so I think I'll leave it there for this lesson. There's another example, and other examples of this are actually a bit hard to come by. They require a little extra thought. I mean, there's a few straightforward ones that Gilmore does, and we'll do that in our next lesson. By the way, this is called an extension. There's an extension. So SU2 is also the extension of SO3 by Z2. That's another way of saying it. So it's not universal terminology, by the way. Sometimes they would say SU2 is the extension of what is it? Maybe sometimes it's the extension of the normal subgroup by this group. But I think the more common language is this group's extension by that group is SU2 because SU2 contains this group as a subgroup, and as a factor group, that's what this group is. So there is this relationship called extension that basically defines this thing. So SU2 is the extension of SO3 by the normal subgroup Z2. So in the next lecture, I'll work through another example that actually goes through what we've done before involving the quaternions that is not literally this example, but it's constructed out of all the pieces here. And we'll do that in our next lecture. It's just to work through this in a much more intricate way where there's a little bit more discrete and variant subgroups going on than just this single one. Okay, see you next time.